today, most of the use cases are around like getting the data as fast as possible into your lakehouse, and then you run some sort of analytics on top of it, which is what predominantly most users use. However, what we want to do is into the future, we also want to help with operational use cases, sub-second use cases, where you are making quick decisions, and those decisions can be sent out to other things or other systems to process. And Anish is going to talk about the transformWithState, which is the new feature that's coming as part of Spark, which is going to help do some of that, right? And so the idea there is to rely on the state management features that are built on top of Spark to help make that decision making. And it has been a little bit inflexible so far on Spark, and with transformWithState, we are adding a ton of capabilities there to make it a little more easier, a little more flexible for folks to adopt and use structured streaming, Apache Spark structured streaming, to run those use cases. So again, the target here is the source and sinks are near real-time data buffers like Pulsar or Kafka, or other sources, for example, the other popular one is Kinesis on our platform. Now, so let's talk a little bit about Apache structured streaming, right? As I said, there's been a 16x growth just in our own platform of folks who are running structured streaming pipelines. Why? Because it is rather simple. You build one code or write one set of code, and you can choose to run it either as a batch or streaming, which is really powerful, right? So it's a unified engine to run batch and streaming at the same time. And we have a ton of fault tolerance capabilities inbuilt on the platform in terms of constant checkpointing, or backing that checkpointing on a durable source S3 and so forth. That helps you to run these pipelines more reliably, and failure happens, you can catch up and run again pretty easily with little to no effort on your part. And performance has been a big an ask from our customer as well. Just as an example, one of our largest customer is able to process 14 million records per second. That's pretty huge, right? Think of this large scale events an NFL final or a World Cup final and things like that. So you would be streaming a ton of data, and the engine should be able to be capable of ingesting and processing that data set. And Apache Spark has been proven to run these workloads pretty reliably, right? And the last but not least, which is what we're going to talk about today, is the stateful processing. So it's not just I take the data, just do some transformation, write it out to a durable engine. You also want to keep that data in memory or in buffer, and as and when event changes, for example, sessionization is a pretty cool use case, right? Everybody knows about it, where I want to understand my customer behavior in my app or my website and so forth. I want to continuously monitor that, understand that, and take actions on top of it. So those kind of data processing is becoming more and more critical, and Apache structured streaming has tons of capabilities there to be able to do that for you guys. So Apache Pulsar integration, right? So we have been working closely with the Apache Pulsar community to create a first-class integration on top of structured streaming and Spark in general, right? So we want to make sure that you are able to read from Apache Pulsar as seamlessly as you would from Kafka or from Kinesis, right? And we also want to make sure that you can use all our capabilities, right? One of the sort of salient features of Spark is you can write in Scala, you can write in Python, you can write it in SQL. No matter where you're coming from, you should be able to use one unified set of frameworks and APIs to process your data. And Pulsar kind of works with all our capabilities as well. And You can use like the popular authentication modes that you use, like the trust store, key store, or basic authentication, doesn't matter. It's all supported on our platform. And last but not least, on Databricks, Apache Pulsar works with Unity Catalog, which is our sort of unified catalog for both processing your data and managing all your models and other Gen AI based assets that you may have. It's a pretty cool feature on our platform. So as on the sync side, meaning I can use Apache Pulsar as a source, but what can I do? Once I process the data, can I send it back to Pulsar? Yes, you can do that. That capability is available as part of Databricks as well. Again, the idea is to doesn't matter where your source or sink is, Kafka, Kinesis, Pulsar, or even Object Store for that matter. We want to make it super easy for you guys to use Apache Spark streaming to read, process, and store that data. But for the stateful stream processing, which is again where the future is, where we are going to add a lot more cool capabilities, I'm going to invite Anish to talk about it. So we are going to do that through our a new capability called transformWithState, and so Anish is going to talk about that.
Awesome, thanks, Jay. So as Jay mentioned, we have a bunch of these customer pipelines, and they're running all of these critical operational use cases. And as he mentioned, there are primarily three parts, right? You have the source part, the sync part, and the transformations that happen in between. And for the most part, for the source and sync, we have most of the integrations in place, right? We can connect to Kafka, Kinesis, Pulsar, Autoloader, bunch of different sources like PubSub. So pretty much whichever cloud platform you're on, or if you're running your own infrastructure, we sort of handle those things for you. But one of the things that was kind of missing in the Spark API was sort of native support for doing sort of arbitrary stateful processing that was fully functional, able to support all the complexity that users or customers needed. So that is why we have sort of built a new API for doing arbitrary stateful processing that will be part of open source Apache Spark. Now, typically, when you think of stateless pipelines, right, they're primarily ETL sort of ingestion pipelines. There is no intermediate state that is involved. You just want to get data as fast as possible from source to destination, and pretty much with whatever auth modes, and maybe at the lowest possible cost, and with the highest performance, right? And most of that is kind of easily natively available through the Spark API, like the data frame API, the dataset API. And then streaming has this nice benefit in Spark where it's natively integrated with the data frame API as well. But then for stateful pipelines, we have to think about how to access the state across various batches, right? So now if we take a step back, structured streaming is kind of based, the query engine is kind of based on this microbatch kind of model, where essentially we plan incremental batches continuously, or depending on the trigger interval, or if you want to do available now, that is also another option. And that will help sort of decide what data is going to be processed in a specific batch. Now, for stateful pipelines, I mean, whatever data you get in a specific batch, of course, is not enough, right? For you to do the stateful transformations, you also need to look back into what state you've accumulated for batches in the past. And for that reason, we allow sort of users to deal with a state which is partition state, or keyed partition state, that is stored on the executors on various partitions, right? So essentially, you can think of the overall state being sharded across a bunch of partitions, and then keys effectively being mapped to a specific partition on those nodes. And then we have the notion of local state, which is effectively backed by two providers. Either you can back it using RocksDB, which is one of the state store providers, or it can be an in-memory HDFS-based state store provider. And of course, because you can be running with spot instances, and the executors can be lost, and they could go down for whatever reason. We cannot rely on the local state as being the final copy of the data, so we have to back this up to persistent storage, such as S3, so that we can use that as part of the persistent checkpoint location, and then resume the query from that point. So today in the stateful stream processing area within Apache Spark, we have two types of operators that we essentially support, right? So one is sort of built-in operators and the other is arbitrary stateful operators. So built-in operators perform like a very specific functionality, like you can think of aggregations, you can think of stream-stream joins, you can think of dedupe, or you can dedupe within watermark. Where what you can do is sort of very explicitly defined, and like you cannot move outside of those boundaries. And then we have something for arbitrary stateful processing, where customers might want to write like their own state machines, or they might want to decide how they want to manage their state, when they want to evict it, what sort of transformations they want based on the specific use case that they have. And today, the only APIs for that is like map group with state or flat map group with state. The only difference being whether you emit certain output from either of these operators or not. Now, we spoke to a bunch of different customers, and as you can see, like the API for flat map group with state is pretty simplistic, right? Like essentially, it's sort of like a Lambda. Users just define like a single function, which helps them to sort of query the state as well as update the state. And the state object is essentially passed to the users as a single like group state object. And then there is no further granularity apart from that, right? So they just define what their stateful processing logic looks like, and then they just update that using the group state object that is passed to this function. Now, we spoke to a bunch of different customers, and we realized that there are a lot of limitations with the existing API that we provide with flat map group with state, right? So a few of them being that we don't allow for actually modeling the state as multiple different types. Like if you want to only conditionally update certain state variables, if you want them to be of different types, we don't support composite types. We force users to do like expensive read, modify, write operations, even if they want to do simple operations like appends or like just want to update a key in a particular map, and so on and so forth. So all of these are like suboptimal, if you will. And then there are some additional features like how you can do state initialization, how you can do eviction, TTL, schema evolution. All these are not really supported natively within the existing API. So one of the reasons why this is the case is because some of these APIs are kind of extensions of the batch API, right? Like, we have had like map groups or flat map groups, which was always part of the core Spark API, and then the natural extension for that was to just add on to, like change the interface a little bit and add on to the underlying state providers or access to the state providers. But we realize that this is not kind of sufficient to solve our customer pain points. And so that is why with the new Spark release, we are working on a new arbitrary stateful API, which is called transformWithState. And transformWithState essentially, again, similar to the spirit of the data frame API, we also will support it in batch mode as well as streaming mode. And it allows you to get access to all the events. You can register timers, you can get like specific callbacks, we allow multiple timers per grouping key, and then we allow fine-grained access to state, right? So we're moving away from this like just single function Lambda kind of model to a much more full-fledged object-oriented model that we've seen like most of our customers require in the way they are building out their applications and running them on the Databricks platform. So similar to other engines, we will provide users access to all the raw input events, the various event-driven semantics that they were looking for, as well as fine-grained access to the state and the state variables. So now there are a few building blocks that you need with transformWithState. One is defining a stateful processor. So now you kind of can define an end-to-end like kind of life cycle where you are going to decide like what class variables you want, what type they're going to be, and I'll talk a little bit more about the various composite types that we support that are optimized for state storage as well as for like improved performance. And then you can also define how users want to create these state variables, whether they want TTL associated with them or not. And then you can define a certain set of functions, right? Like you can do the initialization, you can handle the initial state, you can handle the input rows, you can handle timers, you can do sort of cleanup, resource cleanup as required at the end. And all of these can be modeled using object-oriented models, so you'll get all the benefits of like a model, like encapsulation and inheritance and all those things, so that you can just define some of the base operations once and then just reuse them across a bunch of different pipelines. The only thing that you need that is different across multiple pipelines is just a new checkpoint directory, right? Like, so you can just provide a new checkpoint, and then you can basically run a bunch of your workloads. Again, you can decide what you want to output. You can decide whether you want to generate output from timers, from the initial input rows that you get. You can decide when you want, like how you want to deal with windowing, and so on and so forth. So all of that is available to users to decide. The initial group state impl that we had for flat map group with state only had this, single value kind of functionality or semantic for how users could deal with state. And we realized that that is effectively not enough. It's not performed for different types. So we want to provide semantics where users can model at least the basic type of collection objects. So they can deal with like single value objects or like lists or maps, and then specific operations around like appends or trying to update specific keys or trying to remove specific keys in a map. So those operations are optimized, and we won't require users to actually deserialize and do a bunch of expensive operations every single time. We also now allow for adding and removing state variables within the same checkpoint directory. So if you decide that I want to keep the pipeline running and I don't want to create a new checkpoint and I still want to add or remove state variables, you can do that within the confines of the same stateful processor as well. For event-driven logic, many of our customers are like, we want to do sessionization, or we want to do like sliding windows or tumbling windows, and we want fine-grained control over timers. So we now allow for registering multiple timers per grouping key. They will expire, and we will sort of issue the callback whenever the earliest microbatch is available that hits the expiration timeout. They are deduped. They are part of the checkpoint directory, so you don't have to worry about replays and making sure that the timers will be handled on query restart and so on and so forth. So all your maintenance windows and everything are automatically handled by the query engine itself. We also give you, like through the handle, you can query what timers you've registered, delete them, list them, and so on and so forth. And we also support like adding or removing timers in processing time or event time. Primarily, like most customers do have event time, so they can define those using watermarks, and they know like what the lateness will be, and then they can decide like how they want to evict state in certain cases as well, right? Like if you don't see an event for some X amount of time, then users can decide that they want to go ahead and remove the state. Another thing that we did not support in the past was chaining of operators. So now in append mode, we allow for chaining multiple stateful operators. So you can have transformWithState in event time followed by another transformWithState, or followed by an aggregation, or followed by a join. And what this lets you do is that you don't have to write to intermediate storage again, right? Like, so you don't have to write to Delta or Kafka. If you can do the transformations within the same pipeline, then you can save on cost as well as latency. And with the new interface, you can define what the new event time column looks like. So the downstream operators can do the record filtering, or they can do the watermark eviction based on the values that you have written. Of course, I mean, they have to adhere to the semantics of the watermark values itself. Otherwise, we won't allow for that query to continue executing. But as long as the invariants hold true, then you can basically just continue to run within the same checkpoint. A few other features that we had requests for was in some cases, like let's say you have a list of values, and then people are keeping track of, let's say, group IDs or transaction IDs and whatnot, and they kind of don't want to worry about doing the eviction for each of those items, so they just want to set some automatic TTL on some of these entries. So we now support TTL on a per entry basis for all of the state types as well. And then we will ensure that any expired entries will be evicted and they will never be returned for users in query. As far as initialization, we have customers who want to use the same checkpoint, or rather use one query and that has accumulated some state, and then use the same state to actually power state for another pipeline. So that is also supported now. So you can have a data frame, which is like an initial state data frame, and you can pass that, and you can perform all like Spark specific operations. Like you can do a union by name and stuff like that. You can combine from multiple state variables, and then use that to actually build the state or rebuild the state for a new pipeline, starting with a new checkpoint directory. So many of our customers are doing this where they have like AB kind of like cloned workloads, or like if they've accumulated a bunch of state and they need to move to a checkpoint for some reason. With this new API, we also support schema evolution. So we essentially don't require users to think about schema and how it has evolved. So we'll keep track of the operator metadata, the schema, how the encoding looks like, how it's going to change over time. The only thing users need to do is like define their state through either like primitives or case classes or Java Bean objects. So all the same interfaces that users are used to in Apache Spark. And then as long as the new schemas or the changes that they make are compatible along with the schema compatibility rules that we define, we allow users to just run with the same checkpoint. They just need to restart the query, and then we'll pick up the new schema and they can run from there. The new API will be supported in Java, Scala, and Python. So pretty much most of our like large chunk of our user base effectively relies on these set of languages. So we will support for all of these languages. Along with this, we have a bunch of other native integrations. So now Spark has the ability to also read state. So we have a state data source, which is a batch data source, where we allow users to read committed state for a given batch. We also allow for reading a state as a change feed. So you can do like CDF, where you can define like a start and end. And then as long as you're using changelog for RocksDB or like Delta for HDFS, we allow for reading the state as a change feed. And you can get updates on a per key basis, on a per record basis, and decide how you want to process that downstream. You can also skip certain snapshots if you are not interested in some of those. We internally at Databricks will also support transformWithState with microbatch pipelining, which is our throughput enhancement related feature. And then the new real-time mode, which is a new trigger mode that we are working exclusively for really, really low latency queries, where even stateful queries, we want to do end-to-end latency of less than 200 to 50 milliseconds. So all of these will be supported natively, along with other state management features like async checkpointing, changelog checkpointing, state rebalancing, Spark Connect, Safe Spark, Unity Catalog for assigned and shared clusters, Delta Life Tables, serverless, photons, all of the various offerings that we have within Databricks will all be natively integrated with the new API. Internally, I won't talk too much in details about this, but a lot of work, and you can see most of our work or commits are in open source Spark, so feel free to check out a bunch of these changes. But we've done a bunch of profiling work between physical column families versus virtual column families, various format-related investigations using merge operators in RocksDB. We've built a bunch of secondary indexes so that we can do efficient range scans. We have state encoders for various types of scans now built into the system. A bunch of serialization format evaluations and improvements along unsafe row, along abrow, and a bunch of other formats. How we deal with the operator metadata, state metadata, format changes over time, schema evolution related improvements as well as the layering of the APIs, right? From the state store to the provider to the processor to the composite types, and how it all kind of ties in together so that we can provide the most seamless and performant experience for our customers. So the availability for the feature, we're currently running in gated private preview within DB. The feature is slated to be part of the Apache Spark 4.0 release, which hopefully we are hoping it will go out end of this year or early next year. And then the feedback so far has been pretty positive. Like we've been, like initially when we spoke about some of these operational workloads, and we have been running with some of our customers around exactly these types of use cases, right? Like how one of our customers is doing like sort of vehicle tracking and predictions where the vehicles would be in certain time. So they have some ML related use cases there. Another customer doing like user experience tracking, like how users are, like what experience users are getting from using their platform. Another is like around call center operational health, like how they are kind of tracking the overall health of their business. And one of the quotes is from one of our customers where they're saying that they like the functionality and then they think the functionality would be useful and gives Spark more parity for the stateful features with Apache Fleek. And last but not least, just quick acknowledgements to the query engine team. I mean, of course, I'm just presenting here, but we have a bunch of folks who work on this stuff as well as the open source community for all of their suggestions, feedback, code reviews, and whatnot in this area. And just in terms of future work, you can keep sort of be rest assured that we'll be working more in this area. We have more features lined up, like we're thinking of adding CEP support, state repartitioning, ability to add or remove stateful operators, have some more enhancements like new composite types and other stuff coming with transformWithState as well. So stay tuned to more improvements to the query engine in Spark for streaming. All right, so with that, I think we can open it up for questions. Anything that Jay or me can answer for you folks.
Sorry, maybe very basic question.
Yeah.
Could you highlight, so with an example, so what sort of things could I already do? So I think to remember that so simple aggregates or running average or so, this I can already do with the existing API.
Yeah,
right?
correct.
So the API you're talking about, so could you give some use cases there? I understand there's a checkpointing part that's not there with the existing API, I guess.
No, so checkpointing is one thing. Like, so most of the use cases that we want to target are like the more complex operational use cases that need some custom logic. So, for example, one of our customers is doing like user experience tracking, right? So they deal with a bunch of different event types, and then they see that, okay, this is the time that the user logged into our service, and then they keep track of each and every event, and then they associate that with the user session effectively. And then they decide that, okay, if this is the previous set of events that they have seen, then this is kind of the action that I need to take for those specific set of events. So it's modeled more like a state machine of sorts. Or another example is like a fraud detection engine, right? Like if they want to do like risk or some fraud analysis, then what type of pattern do they need to see for the user financial like transaction activity effectively, right? And most of that is all like custom code. Or one of our customers is trying to predict how they should deploy some of their farm equipment, for example. So what should go where, how many equipment should they add, what is the time that they would need to perform certain operations. So it's more like a optimization kind of a problem for them. And most of the code that they have there is pretty much all things that they have built in. But they don't have the functionality or the infrastructure from the query engine to do like stuff like conditional updates or like modeling the state more flexibly, or doing schema evolution, or doing like TTL, or doing like more event-driven timer logic, and so on. So that is what we are solving with the new API.
I would have another question.
Go ahead. Yeah, go ahead.
So just out of curiosity, the three languages, Scala, Java, Python that you mentioned, do you have a breakdown? What are customers using most?
Yeah, so for most performance-sensitive customers, they do prefer to use Scala. Scala or Java, basically, because there is a perf diff with the Python API, because we have to do the serialization and pickling using Arrow and a bunch of additional serialization work, and then there is like sort of IPC that needs to happen between the main executor JVM as well. But there are a set of customers who do prefer, they're more conversant with Python. Their data engineers and all might be more conversant with Python. So they do tend to choose Python. Some of our customers don't have, they have near real-time latency requirements, right? They could be in tens of seconds or maybe even up to 30 seconds or something, which is kind of fine for them. So for those kinds of customers, they do prefer to use Python. But for large chunk of these stateful pipelines, they do tend to be in Scala. Scala or Java. So it's maybe a 80-20 split. Yeah. Yeah, go ahead.
How do you guys scale, in terms of, do you guys use key-based sharding or something?
Yeah, so the partitioning scheme is kind of based on the number of shuffle partitions. So it's like a hash-based partitioning scheme. So the number of shuffle partitions is kind of decided through a config that the user configures upfront. So we kind of ensure that the same key, of course, lands on the same partition, and then users can do updates from there. But the partition itself is not tied to the executor as such. The partition can move around different executors. So if you add, one is scaling in terms of how many partitions you want to assign to a particular node, right? So for that, we have horizontal scaling or auto scaling with scale up or scale down abilities. And then the number of partitions basically will be adjusted to the available compute resources. And we try to map 1:1 for one partition to one core. So at least it's recommended for you to have the same number of cores as the number of partitions. Today, we don't support repartitioning as such. The only way you can do repartitioning is take the state from one of the queries and use a new checkpoint and use a larger number of partitions. But then in that case, we don't actually clone the offsets. You might have processed till a certain point, you don't want to process that. But that is left up to the user. The user will have to say that, okay, if you're doing with Kafka or Kinesis, then start from this offset, or for Delta, start with this timestamp or this offset. So that is something that we are actively working on. So one of the next things that you'll see is us working on repartitioning or re-encoding, where you can change the partitioning on the fly for the same checkpoint location. And with some of our managed offerings like Delta Live Tables and some of the serverless offerings, you will see us kind of do that automatically for users. So users won't have to think or worry about that. You just set it to auto, and then we'll automatically scale up and scale down and manage the sharding and distribution for you.
How do you guys handle failures?
So failures in terms of executor failures, or?
So basically, if you're trying to process a message and there is an issue with that message.
Yeah, so Spark works on this notion of checkpointing the state initially. So we initially record what is the offset that we are going to process in a particular batch within the offset log. So that is written atomically to some object store, so like S3 or Azure or whatever it is. And then in microbatch mode, so we have different trigger modes, like microbatch mode is one, and then we have a new real-time mode that is coming up. But with microbatch mode, we pre-commit the offsets, rather we pre-decide the offsets and we write them out. And then the incremental batch actually processes that. And then if it is able to successfully process, then it will write an entry to the commit log. So it's like a redo log kind of functionality. If it is not able to write the commit log because of a failure at any point, then when you restart the query, we first check whether we need to replay any set of batches. And the assumption is that you have a replayable source. So you have data, like let's say you're reading from Kinesis or Kafka or Pulsar, for example. The assumption is that, of course, the source needs to have enough retention that the data is available for us to read and reprocess. And once that is available, then the assumption is that the batch boundary itself is idempotent. So we know that it's a deterministic batch. And then for sinks like Delta, we know or we can understand whether we have committed the same batch or the same content as a previous transaction or not. Like if it is already committed, then the sink will effectively just ignore it, if you will. But then we just need to ensure that the commit log or the commit entry is written for that particular batch. And then we move ahead to planning the next batch. I mean, of course, there is more complexity in pipelining, for example, right, where we sort of plan multiple batches in parallel. And then we do dependency management across various stateful stages, right? Like what needs to execute before what needs to complete before what do I need to sort of checkpoint. So all of that is kind of handled completely seamlessly, by our engine. Yeah, correct, exactly, yeah. Sure. Cool, awesome. Yeah, no more questions. Thanks, folks.
Thank you.